Good to see you, everybody. Today I'm going to talk about delegates. This is a intermediate, no, it's a beginners to intermediate level talk. I have no idea if it actually is, but I'm not going to cover the advanced topics of actually implementing delegates. I'm going to focus on how they're used, basic usage, and how we use them extensively inside of IncludeOS. So my name is Alfred. I'm the CTO of IncludeOS. It's a library operating system. So most of you should know that already. If you don't, you can look at this black screen right here. It's flickering a little. Hopefully that's not going to be a recurring problem. Okay. So I actually got into this whole idea of using delegates when I was starting to implement or design IncludeOS, and in particular the IP stack, back in roughly 2014. So what I was looking for was a way to achieve complete isolation between layers, because I'm making an IP stack and the RFCs are pretty strict about that. You're supposed to isolate. I talked yesterday about layers. I don't think you can have hugely long, horizontal, clean layers, but you can definitely have isolation between the protocol handlers inside the IP stack, and that's a good way, I think, to design it. So I was trying to fulfill all these requirements. You know, how can I pass a network packet from Ethernet up to IP4? I don't want any of those classes to know about each other, because that makes it more flexible. I also need to have state in both. So for example, I might have 4 or 5 IP stacks. So they can't be just a global. I just can't keep global state. Ideally, I also want to be able to rewire during runtime. And the main reason for this is that if you make something very hard-coded, you've seen these object hierarchies, I think it's really hard to get right. And I was absolutely certain I wasn't going to get it right the first time. So I thought, let me just implement one class at a time, make a flexible system for wiring them together later, and I can actually make different versions of the IP stacks with different types of wiring, etc. And also the hard requirement, 0 overhead. So possibilities we could use, or we could consider function pointers. You could pass the state around. I think that's what Linux would do, or any C program. Just have normal functions and then pass the state as probably the first parameter in a struct, or something like that. But I don't think it's a very nice object-oriented solution. I was considering stud function. I was looking at that and getting to know that. This is back in when I was new C++. And I couldn't find a way to make them point to member functions. Because that would be, I had this clear idea, if I could just point to a member function, then the state could actually be maintained inside of that instance of that object. Polymorphism, that's overhead. Might not be that much overhead depending on how you design it. I'm not completely against polymorphism. We use it some places, but we try to avoid it in really, really hot paths. And networking, passing packets up and down, that's some of the hottest paths we have inside of IncludeOS. So Google, right? That's what we do. I found this article. It's called Member Function Pointers and the Fastest Possible C++ Delegates. So this is an old article. It's from 2005. It was written by Don Clogston. And it's really impressive amount of detail in there, and it really explains what is actually a member function pointer. Anybody familiar with that? Can anybody just right off the bat write a pointer to a member function? Okay, you guys are good at that. The syntax isn't, it's not perfectly intuitive, but it's good. This is a good introduction to how you can deal with them. Before C++, this was made before C++ 11, so lots of macros in there. And that's, not an optimal solution, so I kept looking. One guy made something that was more standards compliant, not using macros, but it had severe limitations. As far as I could see, you'd have to make a separate version of the delegate for each of the function signatures. This was before the variadic templates, etc. So, you know, but it was something, and then Google a little bit more, and then I finally found this, which is impossibly fast delegates in C++11. You scroll down on that page, it's a nice read. People are super excited, and they're saying it's faster than std function, and it's the speed and the performance is actually identical to calling via a pure function pointer. So no instantiation of an object, not calling via. It's as fast as calling via a single C function pointer. I did some measurements myself, and I found that to be the case as well. The difference isn't huge, but I noticed, we had identical performance to calling via normal function pointer. So copy paste, right? So that was the first delegate implementation for IncludeOS. I said last year as well, I owe the person a beer who implemented this. It was really a good starting point for us. That person never made contact. If you know the person, or if you are that person, please let me know and we'll buy you a drink. So let's look at how we use them. And start with the basics. So this is a very trivial example. I'll get to more interesting examples in a while. We have a nice std function-like signature. So we're just saying delegate. Okay, so that's not optimal for the example. I'm saying decal type to just get the type of function 1, but you could just specify any function signature you would like, exactly like you would std function. And then, it's compatible mostly with the std function. So in this case, I'm actually assigning the delegate to std function, which I'm again assigning to pointer function 1. So this is a trivial example. I'm just pointing to normal functions now, just to get started. And it has a call operator, so you can call it just like you would call a normal function. If you call it when it's initialized, it's much nicer than a function pointer. It's actually going to check for null pointer, and it's going to throw an exception. So that's nice. And the output from here, you can see first we're calling function 1 twice, and then we're calling function 2 twice. So we actually assigned the delegates and the std functions to 2 different functions, and we could change where they were pointing during runtime. So that's kind of promising for the modularity and the flexibility that we were looking for. Lambdas, there are no surprises here, not really. I'm saying auto func, and then I'm creating a lambda here. And in the case of the delegate, I'm actually specifying the signature of the lambda, and then I'm specifying the body of the lambda, and I'm calling both of these. And the results are exactly as you would expect. Some slight things you might notice. If you say auto and this function, it turns out you can't reassign because it defaults to const. With delegate, obviously, you can't use auto because auto would resolve to, and if you say auto and the std function signature, that would resolve to a std function and not to a delegate, obviously. Are you with me so far? This is okay? This is completely trivial, right? Yeah, so I'm keeping my promise of making this a beginner level talk so far. So let's do the more interesting part and actually delegate stuff to member functions. And for this example, I'm making a neuron. You guys are familiar with neurons? They are the tiny little cells inside of your brain. So if you look at that little tree structure there in the center, that's the center of the cell body. It will receive electronic pulses at the bottom, I think, and it will build up a charge inside the cell body. Once it reaches a certain threshold, it will actually fire to all of these terminals up the tree there. So that's essentially how your brain is wired, right? So we'll make a tiny, tiny little brain for this example. So we can look at the implementation. I'm specifying the type of a delegate. So I'm saying that the delegate I want for actually having one neuron fire to the next neuron, it's actually just a function that doesn't return anything, but it takes an integer as a parameter where the integer represents the charge I want to transmit. And then I have the actual delegate member. This is a public member. I don't know if I'm breaking any core guidelines here, but for the sake of example, it fits nicely on the screen when you don't actually just have a setter for it. But the point is that you want to be able to wire the neuron from the outside. So I want to be able to say this neuron connects to that neuron, and that neuron connects to that neuron, and etc., and build up kind of a structure in that way. So this is the algorithm for receiving an impulse. I'm incrementing my charge, and then if the total charge for my neuron now is above my threshold, or if above and equal to my threshold, and if I actually have a delegate to a next neuron, then I'll actually just call that delegate, and I will send my charge. And I'm removing some of the charge here because you can imagine it costs a little bit. I can't imagine in your brain every time a neuron fires that it just keeps that all the electric charge just stays there. I'm guessing there has to be some loss along the way. So is it okay? It's a simple program. So let's make a little brain. So here we instantiate 3 neurons, neuron 1, neuron 2, neuron 3. Of course, these are very simplified. A normal neuron would have hundreds or thousands of connections, but these ones have only one, so they're very simple neurons. So we instantiate, and this is how you wire them together, and this is actually how you assign a delegate to point to a member function. So I'm saying that neuron 1 has a fire target. I'm assigning the fire target of neuron 1 to neuron 2. So I'm specifying first the instance I want to point to, and then the address of the member function. Okay? And the same goes for neuron 2. I'm assigning neuron 2 to fire towards neuron 3. And then I have a small little for loop where I'm firing pulses, but I'm only firing pulses at the first neuron. Okay? So the idea is that I want the firing to happen into neuron 1, and I want it to build up a charge after a couple of firings, and then it's supposed to fire to the next neuron. That's supposed to build up a charge, and then that is going to build up a charge and fire to the last one, etc. The result is like this. So it's as expected. The first pulse, the first neuron reaches a charge of 50. That's half its capacity. So nothing more happens. Pulse 1 happens, the second pulse, and then N1 reaches its threshold and it fires. And now N2 is charged up to 50, and so on and so on. And at the very end, you can see that the third neuron finally also reaches its capacity, but it doesn't have anywhere to go, so I guess it just keeps its electric charge until it blows up or something. Is it okay so far? So I'm making a tiny little neural network out of delegates, wiring neurons together using delegates. So rewiring these during runtime, that's interesting. That was a requirement I had. I thought that was kind of I thought I could see use cases for that, and we're going to look at an actual use case for that in IncludeOS later. So what I've done now is added another class. So I think it's one of the things I like the most about these delegates is that it doesn't know about what kind or what type of class it's pointing to. It only knows about the signature. Have you noticed? I never told the neuron that it was actually having a delegate that was supposed to point to another neuron. It was just a delegate pointing to a function signature that had a void return and integer parameter value. Okay? So that's really cool. You can wire these any way you like as long as the function signature matches. And in terms of information hiding, I think that's really great. You know, it means you can make really, really isolated components. All they have to do is, they have to know about the signature of the one they're talking to. So this is a completely new class, but the function signature is the same. And I also named it differently just to make it extra clear. So now we have the initial wiring. It's the same as before. A neuron 1 fires to neuron 2, neuron 2 fires to neuron 3, but then now neuron 3, it actually fires to this ground, or to terminate, or the bucket at the end where you can actually take all the electric charge. And more interesting is that, you know, we are doing this algorithm and we're sending the initial pulses and we're sending it only to the first neuron, and it builds up, you know, and it spreads throughout that neural network. But then here we actually do a rewiring and we haven't restarted our program. So the programming is still running, but now I'm saying that neuron 3 should instead point to a completely new neuron that came out of nowhere. You know, your brain was so lucky today, it actually suddenly got an extra neuron, and now neuron 3 actually connects to there. Okay, but then neuron 4 now connects to the terminal instead. And the results are exactly like before. So it's a bit hard to see probably. I think we are here just seeing that at the, probably we don't get all the results, but at the end at least you could see that I've woken up neuron number 4. And neuron number 4 wasn't there in the first iteration. Okay? So I'm still just doing all the firing towards neuron 1, and neuron 4 suddenly was becoming part of this neural network during runtime. I think that's an interesting observation. So they are completely anonymous, for free, flexible object coupling. I guess that's one thing you could use to describe it. Could we do this with the stud function? Some people pointed out stud bind. Stud bind has a way of pointing, or you can create. What are they? Are they variables? Are they functions? You can create a function, auto F3 here, and you can bind it to the member function of a class. But the interesting thing I said, because I said, what is it? You know, and it's actually interesting that the return value of bind is, it says that it's a function object of unspecified type T. So that means you can't assign it to a stud function. So there might be some tricks here, but I didn't find any. I tried to assign it to a stud function and I wasn't able to. And also if you look at the signature, it's not nearly as nice in my opinion. It's nice for other use cases. I'm able to, for example, fixate the parameters or fixate some of the parameters while leaving other parameters flexible. So in this case, I'm fixating the parameter 95, but I'm using a placeholder _1 for the last parameter, and then I'm calling it with only one parameter. So I've fixated the first parameter, but the last have kept flexible. So there might be some black magic or some tricks you could use to actually use bind in this context. I haven't found it. These Legos are smelling an opportunity. They want human brains now, because I showed you now that I can make a neural network. So maybe we should try to make a human brain. Yeah, it's hard to think with only 4 neurons. So we could try to do that. I was actually considering doing that for this talk, but it turns out you need 86 billion neurons to simulate a human brain, and you need, I don't even know how to mention that number. It's 0.15 quadrillion connections, and that averages on to 1,500 connections per neuron. That means if each of these neurons needed 16 bytes each, you would need 2.4 petabytes to store all of them. If you had 16 gigabyte computers, you would need approximately 2.4 petabytes of memory, and you would need 150,000 of these computers to store those neurons. So that would amount to approximately 9 billion watts per machine, but the human brain uses only 20 watts. I just thought that's quite interesting in case you were considering making a human brain with these little techniques that I've showed you. So I don't think that's viable. Yeah, so you're not getting the brains, unfortunately, but we can use this to implement an IP stack, and that's quite a lot more complex than the little neurons I've made so far. It's not as complex as a brain, but it's certainly a complex machinery. So let's look at how we are using delegates to wire the IP stack inside of IncludeOS. And this is actually just snipped from GitHub. You can go and see, it's all open source. You can see how we're doing it. And we are first, at the top, I'm actually just making all these delegates. So I'm saying that each of these protocol objects, they have a top and a bottom. And I'm saying that the network interface, it receives an ARP packet at the bottom. And that ARP packet should then be delegated to the ARP handler. When the network interface sees an IP4 packet, because it investigates the Ethernet header, well then, that type of packet should be delegated to the bottom of the IP4 protocol handler. Similarly with ICMP, with UDP, and with TCP. And then we go the other way down, and we do the same type of wiring, but then for the return path. And also for the path where you actually initiate packet creation inside of your own machine. So one interesting thing, I thought it was very hard to decide when I made IncludeOS, should I do context switches right off the bat? Should I start with threading? It's not obvious that you shouldn't, but I thought it's nice to see how far you can go with only one thread. So I'm going to just briefly look at how these delegates work in a callback-based system. So this is the event tree. This is actually showing a graphic representation of the wiring I showed you in code. So this shows you how all of these protocol objects are connected together using delegates. And remember that I can rewire these anytime during runtime. Right? And it's also very easy for you if you think that you want an IP stack where you don't need HTTP or you don't need TCP or you don't even need ARP. You're making a completely different IP stack. All you need is to make a new small wrapper object like this, the INET internet object that I showed you code from, where you actually rewire it differently to your own tastes. So what's interesting here is that the full event path, and now I'm trying to address the question of how callbacks and async works as opposed to preemptive multitasking. And it's interesting here that when we have used these delegates, the full path of all these events, it's already laid out in memory from the get-go. And it's also then possible to create new paths during runtime. So at the bottom, you'll see an interrupt happens. And that's why I find this quite natural for the computer to actually work in this way. Because if you don't have a classical operating system kernel that's doing multi-processes in between, we're just putting these delegates directly on top of the interrupts. Okay? So if you think about what happens when you receive, when you click on includeos.org and you receive the web page, what's happening? I mean, it's a sequence of events. It's a cascading sequence of events where lots of smaller events happen in the subsystems, and they are actually building up state quite like the neurons. So I've tried to represent this by having a thicker arrow for the delegates that have been called more often. And we're now imagining that I'm receiving a network packet on the network interface that's triggering an interrupt handler. And now, of course, we have a choice whether we want to preempt the driver and actually say that, to call the driver and force the driver to actually fetch our packet and handle our packet, or if we just go up to the event manager, which is what we are doing by default, and just set a little flag saying that this interrupt has happened, so I will need servicing, and that whenever the event loop gets back to you after having handled its previous event, it will then actually call a delegate. And you see these blue lines with the rings at the end. I'm using those to represent delegates. So the event manager knows that the interrupt has happened, and it calls a delegate to the driver that's subscribed to that particular event. The network driver has a delegate pointing to the Ethernet object. The Ethernet object has then a delegate pointing to the ARP handler. So that's the first packet you're likely to see if you recently booted your computer. So the network gateway who wanted to send you this response from Google, it would ask you what your MAC address was, etc. But then we traverse the path and we go up to the IP4 handler, not much state in there. But when you get to TCP, there's a buildup of state. So there will be a first packet that you will be getting, or depending on who initiated the connection, assuming they're initiating the connection, you'll first get a SYN packet, you'll answer with a ACK packet, and then you'll get a SYN ACK packet. And that means several events are happening in this subsystem, quite like with the neuron example. I'm building up state inside of TCP, and TCP then might start reading. Or actually, it's now in this case, the HTTP is subscribing to events from the TCP connection, and the HTTP handler is going to start reading, and not until it reaches the point where it has actually received a full HTTP request is it actually going to trigger something to happen up in user space. Yeah. So on this next slide, I've tried to show that I've kind of heated up the protocol objects that have received the most attention. So some of these objects have gotten more packets than other, and you can see that TCP is probably the hottest one in terms of state. It's keeping up a lot of state and building up a lot of state. So if you look at callbacks as lambdas, that they are nesting lambdas inside of each other, then it doesn't feel like it's very natural for the computer. But if you think about callbacks as delegates that you're wiring like this, I think it feels quite natural for the computer, actually. When it comes to performance, this is also another reason why I think it's a good idea to start with a callback-based asynchronous system. It turns out, or actually this is from John Bandela. He did a talk last year where he did some performance measuring. Really interesting talk. And he was comparing callbacks versus Go channel versus boost fibers versus student futures. And the results were quite grim. Callbacks were really hard to beat. But everybody agrees that callbacks aren't great, and I'm going to get to an example where it really, really gets messy, even with the delegates. So our assumption is that the zero overhead choice, which is what we're looking for all the time, that the zero overhead choice is to start with a callback-based system. There is no context switches. There is nothing else going on. I'm just following the path laid out by these delegates, and that's all I'm doing. But our assumption is that having channels or something similar built on top of stackless coroutines is probably going to be an equally performant alternative with probably, in many cases, some more intuitive way to program. So it's not always smooth sailing, and this is an example of that. I'm going to get dizzy trying to explain this. So we're using a lot of delegates here, and what we're trying to achieve is to transfer file A from connection B chunkwise when both the producer and the consumer are callback-based async. Okay, so that's when it gets kind of hard. When you have all these linear event paths, it's quite easy. When you try to make loops in that event tree, it turns out it's much harder. Might be some new abstractions we can use, but so far this is something we came up with. So this is, I didn't implement this, a couple of kernel developers on our team did. So essentially you start by making a lambda, and you have a shared pointer to this lambda that will function as a sort of a job controller. And you have to then keep in mind that everything is async, so you can't preserve anything on stack. The stack frame goes, it gets destroyed the moment this function returns. And actually, yeah. So, but you can pass stuff in. So we're passing in. We're preserving a weak pointer to itself inside of this lambda, and then we pass. We actually produce a shared pointer to ourself, and then we do a call to the read to the file system. We actually do that call, which is also async. So then we have to pass in a lambda that's holding a shared pointer back to this original caller, and you can see this seems quite messy. And if we're done already, then we return, and it continues. We pass a shared pointer back to next to the consumer callback. When the consumer is done, it calls next, asking for the next chunk, completing the actual loop. So I've made some graphics to try to explain this even better. But as you can see, I don't think this looks linear or intuitive in terms of programming. So and all this algorithmic stuff, it's really hard to keep track. Where am I? Which part of the sequence am I in? Because it's absolutely not sequential when you have lambdas nested inside lambdas and nested inside lambdas. And then, of course, the actual starting of this loop starts at the very bottom. So, fortunately, the real brains are even messier. So, these mouse neurons, these are actually mouse neurons that have been generated, I think, automatically into 3D renditions of real neurons, and yours are even worse. And I think that there are also lots of loops in the real neural networks. I'm certain that in my brain there are lots of these feedback loops, and yeah. So let's look at how this algorithm actually works. If we try to organize it a little and pull these neurons apart, and it doesn't really get much nicer, but what's nice is that, essentially this next, that's a lambda that actually just represents a kind of job. And it holds a weak pointer to itself, and it's able to, from that weak pointer, produce shared pointers to itself that it can hand to the producer and the consumer respectively. And what's nice about it, of course, is that once this whole shifting, or once this whole loop is finished, it will actually, the reference count will eventually go back to 0. So there will be no more shared pointers pointing to this next function, and it will actually just disappear. So it's quite nice. You have all these events happening. At some point, you trigger, you need to trigger a transfer event where you're trying to hook up a loop between two of these various events happening, and this is one way of doing it, but it's absolutely not intuitive to read. It took me quite a while to actually just try to parse that code, because it's in that sense very different from how our brain works. So all of that would have been possible with a very simple for loop, using stackful fibers and blocking calls. So we're not arguing. We're not trying to convince everybody that the callback-based solution is the perfect way to do it, but we think it's the zero overhead solution, the simplest, least complex way to do it. And what's also interesting is that with our current solution, we are able to handle multiple thousands of connections concurrently with 0 context switches and using only a single stack. And that's, I don't know any other way we could have done that. So if you don't like the algorithm I just showed you, if it puts you off, I mean, we don't run into that a lot. You'll run into it every once in a while where you need this solution where you have 2 async events that are supposed to be hooked together. But there's an interesting library called ELD, and that's built on top of Boost ASIO. And this is formerly it was its own company. It's now acquired by Docker. So they've built a really nice, their aim was to actually alleviate this, or to remove this whole callback-based programming paradigm. So they built something on top of Boost ASIO where everything automatically just gets fixed for you so that you can write your code very sequential. And they have implemented Boost ASIO backend for IncludeOS so that they were able to run this library on top of IncludeOS. The integration isn't complete, but they have been able to do it. So then you can get stuff like this, where you just say you want to perform a HTTP request, and you say R finalize. You deserialize whenever it's done, and when you do finalize, that's yielding code. So it's a cooperative multitasking, where it will just yield, and then it's going to be a stack there that's going to be switched out, and something else is going to be switched in, and they have a whole scheduler system to deal with all that. And of course, no callbacks. So even if we build a callback-based system using delegates to connect stuff, it doesn't mean we're stuck with that. You can have stuff like this on top. So let's take another look. This is the typical thing you associate with callbacks. At least it was for me, coming from, for example, Node.js. If you've ever used Node.js and looked at examples, you'll see a lot of this. And that's kind of, you have level 1 of Lambda here, and then you have level 2 of Lambda there. And the problem is that it looks sequential in the sense that it is syntactically sequential, but obviously during runtime, this is not necessarily the sequence of events. So if you're looking at it like this, I mean, we're essentially doing the same thing. I'm just saying that whenever, I've just actually phrased the name of the functions differently here. So what I'm saying is that whenever TCP wants to transmit a packet downstream, then you want that to go to IPv4 and not to the top of the IP4 object. So if it's possible for you to instead of nesting lambdas like that, but if it's possible for you to use delegates and to have one protocol object point to another protocol object, then it doesn't necessarily have to feel as async. And this is, of course, sequential code, although the underlying system is completely asynchronous. So it's also nice, of course, that these objects don't know anything about each other except for these delegate signatures. Another really interesting and nice feature you get is unit testing. So in this case, we're actually unit testing the IP part of our IP stack. And this is something we're doing in Linux user space. So this is a snippet from one of our unit tests. So we instantiate a mock link layer. It's just a mock of the network interface card. And since it's using delegates, it's really easy to create that mock. And now you can build a full IP stack, instantiate a full IP stack on top of that network interface. And then we can rewire this IP stack for testing. Instead of rewiring it for actually talking to real protocol handlers, we can wire it to call mock protocol handlers. So that's what happens here. So you can see that I'm setting the drop handler. IP has a drop handler. For example, it's getting a packet that's where the source address is broadcast. That's an illegal packet. You can't come from broadcast. You can send to broadcast, but not from. So IP has a drop handler that it's going to by default send packets to that drop handler, so we can keep track of how many packets are getting dropped and why. So we're making a mock drop handler now, and we're just saying, well, I don't want to do anything with this packet except I want to increment the counter, and we can then make a expect drop macro on top of that. And now when I send a packet to the bottom of the IP stack, completely synchronously, it will be just dropped, and it will be the drop count is going to increment, and that means this unit test can then pass. So some observation, delegating to a lambda, it allows you to pass state via capture clauses, which is what we used in the async for loop. I don't think I was able to explain all the details in that async for loop, but it's not actually the purpose of the talk, but you can take a look. It's The point was that it's using delegates inside, no, using lambdas inside of lambdas is not the easy or intuitive way to program. And they can look deceptively sequential, although they're not. If you design as a tree of event paths, it might be simpler. It's not necessarily that you can always do it like that, but in our case, it was possible to do it like that, and it feels quite intuitive to work with. Yeah. So I'm getting close to the end, but I'm going to show you an example of something we can do with IncludeOS, where we can actually do something real here. So this is from yesterday, a simple web service, and you can see that we're using a simple HTTP server abstraction on top of our IP stack. And the first thing you'll notice is that this is service start, and it's async in the sense that when service start starts, you're supposed to just exit right away. So what you're supposed to do inside of that service start is just to hook up events hook up event handlers to events. And in this case, we are hooking up a very complex chain of events by saying that we want there to be an IP stack, and on top of that IP stack, we want there to be an HTTP server. And now I'm using a normal callback system here to say that when this server receives a request, this is what I want to happen. I just want to the response object that's being provided for me, where all the delegates going downward are wired already from the HTTP response all the way down to the Ethernet network interface. I want to write just some HTML down that return path. And now I'm saying that I want the server to listen to port 80. This is just a simple HTTP abstraction. And then the event loop exits. You boot -- create bridge dot, and we get hello web. So I showed this yesterday, no surprise. So yeah, this is how we do configuration. This is just an aside. We do configuration now outside of IncludeOS and not inside of IncludeOS. So if you have used IncludeOS in the past and you have noticed that you had to do configuration in the code, we've changed that now. So we're actually now building the configuration into the binary, but it's that much nicer for maintenance. So, and that's also one of the reasons why we've made a cleaner abstraction below the link layer in order to be able to switch out drivers without having to change code. So anyway, let's do something more interesting, using delegates to rewire. So what I'm doing now is that it's essentially much the same thing, but so I'm making a web server. I commented some of it out in order to fit everything on the slide. But what I'm doing is that I'm actually now talking to the IP stack, and I'm getting the network interface card object, which is also an Ethernet handler, and I'm saying that I want to reassign the IP4 upstream to this new IP4 handler. And this new IP4 handler, just like in the unit test, in this case, is just a dumb function, right? But this means that I'm able to now reassign how these delegates are wired. And this is actually the way we would go about implementing a firewall and hooking a firewall into the IP stack. So you can do this, and then in this new IP handler, you can see that it has to respect the signature of these upstream and downstream delegates that we use for our IP stack. But essentially, it just takes a pointer, or it's a unique pointer to a network packet, and that unique pointer is going to get moved into this function. So I'm also now I'm casting this pointer. So I'm doing a unique pointer cast because I know that this packet is in fact an IP4 packet. So this might seem strange to some of you that we do these typecasts, but that's actually how the packets. How I think it's natural to treat the packets. A network packet comes in, and you actually have to investigate the type of the packet by looking at the type field in respectively the Ethernet header and then in the IP4 header. So you have the whole buffer already, but you don't know what kind of type it is until you are in runtime and you're actually inspecting the contents of that packet. So there might be other techniques we could have used, but we've made sure that we have safe ways of doing typecasts. And I do have a guarantee from the lower level that since I'm the IP4 handler, they have already checked and made sure that this is in fact an IP packet, and that's why they called my delegate, because I was the IP4 packet handler. So all I'm doing here, I'm not doing anything very interesting, but I am inspecting the actual packet, and I'm retrieving the IP address from inside of that packet. So I think that's also quite an intuitive way to do it. We have packets, and that's just a completely normal class where you have getters for all those different fields in the IP header. What does it mean? 15 minutes? Yeah, that's fine. Thanks. So we're not doing much interesting here. We're just saying that we want to print out who this packet is coming from. Obviously, what you could do here, if you wanted a firewall, was to just say, okay, let's look at this IP address, and if it's from that person or that person, then we drop it. You could look at again inspect what type of packet this IP packet is. Is it UDP or is it TCP? And you could inspect the port numbers. So you could actually go from here and build a complete firewall. And at the end, what I'm doing is I'm just pushing that stack. Now I'm pushing that same packet. I'm actually moving it directly up to the actual IP handler of the IP stack. So now I'm saying I'm done with this packet and it's fine. I've checked that it's okay. I didn't drop it. If I wanted to drop it, I would just return. And the packet would just go out of scope and be released, go back to its buffer store. But in this case, I'm actually just pushing it back up to where it was supposed to go in the first place. So this is how packets are being pushed around in CludeOS. And so let's see how it looks. Yeah, interesting though is that I'm keeping this server, right? Because I'm keeping the path from the NIC and all the way up to the HTTP server. I'm keeping that path intact. All I've done is to plug something in between. Right, so in between the network interface card and the original IP handler, I've just plugged my own function in between so that I can lie there and inspect the packets. So the result when I boot is still a normal web server, but inside of the terminal, you will see that it's actually printing out that it received packets from the gateway, in this case IP address 10.0.0.1. Yeah, that's actually all I had. There are a couple of more talks. There is one talk tomorrow by the guy who implemented our delegates. So if you have questions about the implementation of the delegates, that's the guy to talk to. I don't know if he's probably not going to cover that tomorrow, but that's the guy to talk to. There's also one talk tomorrow by one of our developers, Ingve. He's going to talk about tools and techniques to stay up to date with modern C++. I'm going to go to that talk. I think it's hard to stay up to date. But please come find us. And if you have any questions, I'll be happy to take them. Any questions? No?
I was curious, why did you choose to create packet pointer type as opposed to packet IPv? You said that it's guaranteed to be IPv4. You make that guarantee when you set that delegate handler.
Yeah.
So what's the reason you use pointer anyway?
Do you mean for the packet? The packet has actually come in a predefined buffer. So the network driver actually has a buffer store of pre-allocated buffers, and it has to have that because we use DMA. So that means the physical device is actually going to lift packets directly into my memory. That means I have to have already a data structure with buffers populated, and the buffers have to be appropriately sized for actually any type of incoming packet. So we use roughly MTU sized, usually they are 1500 bytes. So you have to kind of pre-allocate those. So it's a bit complicated, but that means we have buffers that are pre-allocated. They have been populated with data by the actual device, and then the natural way is to use some kind of pointer. We used to have a shared pointer because we thought we might need to have several copies of packets. There are places in the IP stack where you, for example, need to buffer. In TCP, you're supposed to retransmit if the retransmit timer fires. That means it hasn't gotten a response in a certain amount of time. So initially we thought, maybe we need to hold on to the packets. Turns out there is quite a lot of overhead with these shared pointers and passing them around. So we ended up figuring out that most of these cases where we thought we needed to retain packets, we could actually solve that in a different way. So now we're just doing a unique pointer and we're moving that unique pointer so the packet that way moves from one protocol handler to the next. Anything else?
What iterates packet rates?
Packet rates. I haven't measured packet rates. We have for one core. I've measured throughput roughly, and it's in the few gigabits of throughput. This is what we can push through a single IncludeOS, a unikernel on a virtual machine with a single core.
No.
If you do we did iPerf. I've done iPerf. So we've also done load balancing experiments with at least, I think, 65,000 concurrent connections, thousands of connections per second. It's quite fast. Obviously, when we're bound to, the way we're using it by default is that we're using a single core, but we also do have access to several CPUs. We don't have high-level abstractions for that yet, but they're in the making. And on this conference in Germany, I'm going to talk about how we can actually do parallelism inside of IncludeOS. And there are several interesting opportunities available to you when you are in complete control of the hardware. We don't need threading. You can actually put functions directly onto cores, for example.
Do you think happens in one interrupt context?
Oh, interrupt context. No, we can go back to the slide about the event handler.
You choose preemptive.
We could choose preemptive. There are some things we do preemptively. Let's see, I think it was here. So when it comes in, you have a choice. I mean, of course, the interrupt actually preempts. It always does. There is no way around it. That's what an interrupt is. You can't prevent it from preempting. What happens here is that there is a preemptive interrupt handler for IQ37, but it's handcrafted to do nothing except setting a bit that's available to the event handler, and we do that atomically. So that means you don't actually have to do a complete context switch, because you just write. You keep track of which registers you're actually clobbering, and you're making a small, very, very easily maintainable and tiny little assembly function that just sets this bit, and then it returns using IRET. There are some things that we are doing preemptively, so you can do context switches. For example, we have a stack sampler. That's quite interesting. If you set a timer to one of these interrupts using one of the timer features in the CPU or one of the timers that are available, you can set an interrupt to happen at a fixed interval, and now when you're preempting, you're on the same stack. So that's quite interesting, because now you're preempting, you're on the same stack, and you can just investigate the stack frame below you, and you know which function was running right now. So we demoed that. I think we showed it last year, but that's one of the things we are doing preemptively. And from there, it's not hard to implement. You could easily put threading on top of there. I mean, we already have the context switching features, most of them in any case. But the complexity explodes, obviously, when you do it. So our mission was to see, how much is it possible to do with this single-threaded, very strictly event-based context. And then we are now, doing experiments with running, for example. We are actually doing experiments where we have several CPUs, and we're assigning, for example, TCP connections to individual CPUs where they can do TLS decryption, etc., on individual CPUs. So we're trying to avoid this classical context switching scenario. mainly because for virtualization, it turns out that multi-threaded applications running in virtual machines perform much worse compared to single-threaded applications as opposed to when they're running directly on bare metal.
So then, like a TCP delegate gets called into last second, so there's a configured core.
Yeah, that's a way to do it. You can have, yeah. I mean, that's a possible way to do it. But there needs to be some kind of event handler on that other core, and I think you could implement something like a thread pool on top of there. So we've done experiments similar to that effect, where you have different CPUs are actually just fetching connections from a shared pool. Another way we have done it is to actually have separate IP stacks running on different cores. So we have some interesting experiments and some results that we would like to share, but they're not ready yet. But the code is there, so you can go look. There are some examples of SMP of running actually just a Lambda on a separate CPU core. There are examples of that in our repository. Yeah.
Can you reassign the object pointer separately from the function pointer, like if you're for the delegates? Like, is it
you can
define them both at the same time?
How do you mean?
So, like, if you have an existing delegate, can you just switch the object to delegates to without switching the function?
Switching just the object, can't you do that? He's shaking his head. I mean, you mean shifting? So, for example, if I had TCP connection object and I want to switch the delegates from pointing to one object to another object, is that what you mean? But to the same function?
Yes.
Yeah, that should be possible. Yeah, because it holds a pointer to the object and to the function.
Yes, you write both again. But you have to write both again.
You won't just replace one object the same time.
Sure, I understand, but I guess I'm trying to figure out what this gives you over just capturing your object in a lambda and then
Okay.
Nothing. Okay.
It's exactly how it does it.
Okay.
Other questions? I guess, please just come up and talk to me if you have other questions. I'd be happy to talk. If you have other questions regarding IncludeOS as well, that's interesting. And don't be shy to come into our chat room. I mean, we really like to have people approach us and connect with us, and we'd be happy to help you if you're interested and curious. Also consider using IncludeOS just as a network library. It runs fine under usage-based Linux. We also have a project now where you can attach the whole IP stack on top of a Linux tap device. So that Linux has a facility where you can pull Ethernet frames directly out from the kernel without going through the Linux IP stack. So it's possible to use IncludeOS in your normal process as an IP stack, and many interesting things you can do with that. Okay, I think I'll just say thanks and.